All right, we are group 15 and our project was the white box fuzzer. So first of all, what is fuzzing? Fuzzing is a software testing technique used to debug code. This basically consists of repeatedly feeding input to our source program in order to find inputs that will crash that program. This is particularly useful for testing programs that take in a structured input. In our specific case, our fuzzer assumes a program that takes 3 ASCII character input arguments. We use the inputs to check corner cases and then monitor the exit code value to determine if the source program crashed. Now, there are 3 main types of fuzzing. First, we have black box fuzzing, which assumes no knowledge of the source program. The implementation of this is basically a brute force method, using randomly generated inputs to find the crash. Then there's white box fuzzing, which is what our fuzzer is meant to implement. This assumes full knowledge of the source program, which means that we can use that knowledge to generate our inputs more intelligently. Finally, there's gray box fuzzing, which is somewhere in between black box and white box.
So let's talk about our design decisions. We used Java parser library to parse through the tree. The library allowed us to use a data structure called abstract syntax tree, also known as AST. The AST data structure allowed us to discover string literals, integer literals, while statements, for statements, and if-else statements. We used these literals to generate our input. Let's look at an example of a while statement. The while statement has 2 children, where the left one is a condition and the right one is a statement. Both then have 2 children, which allow us to access the variable names, the constants, and the operator in the while statement. The advantage of this traversal of this tree for a particular literal only takes 1 time, which will be done in O of n time, because you need to traverse every node.
Other data structures that we use includes an array list, which allows us to store general information about the source code to generate inputs. We also use a hash set. This allows us to create a set that does not contain any duplicates in theta of n time. Similar to a hash set, a tree set lets us efficiently create a set without duplicates, but also has the property of being sorted. This takes O of n log n time. Now let's talk about how we use the parsed information. For the case of strings, we identify all of the strings in the code and test them as inputs. We store all of the tests in a hash set. This allows us to make sure that we don't use duplicates. For the case of numbers, such as integers or doubles, we identify all numerical values present in the source code. We then test random intermediate values as well as the values presented. Finally, we repeat this for all the numbers that are negative. We also have special cases that we can solve, such as string concatenation and comparisons in conditional statements.
Okay, let's take a closer look at why we're parsing out these numbers. We can see on the left-hand side here a relatively standard conditional statement where I is essentially the integer format of arg0, and we want to execute this code because maybe something crashes in here, so we want to get in there with our input. We can parse out all the numbers and end up with a sorted array 9 and 15. But if we were to insert any of these numbers into here, it wouldn't actually enter this statement. So what we're going to do is we're going to add these intermediate values 4, 11, and 20 where they're generated at random within the range. One on the left-hand side, one between the 2 numbers, and one on the right-hand side. And this can be extended to as many numbers as you want. We can see that then when we insert these as inputs, we will with one of these enter this conditional statement and execute this code, possibly finding a crash. And you can convince yourself that if any of these greater than or less than signs were switched around and or whatever, that this would still work to get inside this code. Now, obviously, just because we got inside that code statement doesn't mean we're going to find a crash. Consider this. In this scenario, we added this one line of code, and now if I is equal to 14, we just crashed our program with a divide by 0 due to this statement right here. So we'll do the same thing that we did last time, but now our first guess with these random numbers of 11 didn't do the trick, because this is the number that would have gotten in, and that's not 14. So we wouldn't have found that divide by 0 error. So what we're then going to do is, after we've tried all of these, we're going to fuzz these by doing a random plus minus 2. So that might plus minus 0, it might plus minus 1, it might plus minus 2. It has the option to do any of those at random. And so we can see after we do that first one, maybe we still don't quite find a 14, right? So we'll do it again, but this time we'll increase the range of the fuzz. So it'll now fuzz by 4. And now here we did find a 14. So on this iteration through these inputs, we are going to find that divide by 0 error. We're going to then continue this pattern by plus minus the previous plus 2 until we either find an error or 5 minutes is up, assuming we didn't find that 14 with the plus minus 4. And this just assures that we're covering a gradually larger amount of fuzzed inputs to attempt to find any of those possible edge case errors.
So here's a diagram that represents the workflow of our implementation of a white box fuzzer. The main file calls the fuzzer, which calls the input generator that uses the information gathered by the file parser. The fuzzer is what actually tests the source code and uses the generated inputs from the input generator. The input generator uses all the integers, doubles, and strings gathered by the visitors from the Java parser library to generate inputs. This is executed until an input that causes a crash is found or the time constraint of 5 minutes has passed.
We are now going to explain briefly how our fuzzer solves a certain code snippet, and then we are actually going to get to see the fuzzer solve it. So if we look at this vulnerable piece of code right here, we're going to see that right here we have a potential divide by 0 exception if I is equal to 7. So first thing we're going to do is we're going to go through this code and we're going to parse out all of the numerical values into a sorted array with no duplications, and we're going to end up with this. We're going to then insert intermediate values between each of these numbers and have an array that now looks like this with these inserted numbers. Next, what we're going to do is we're going to send these as inputs. None of them are going to throw an error, so we're going to fuzz this data by altering each number slightly at random, and we're going to end up with something like this. And you can see 7. So when we run this as an input into our program, then we're going to get that divide by 0, and we have successfully found an error. So let's see what this looks like in actual application when we run our fuzzer. So right here you can see that we have that same code that was just written out. So if we run our fuzzer, it opens up the GUI and we can go actually select this file. So we can go through the file system and find it real quick. So over here, test files, and right there. So we hit run, and now this is going to take a minute since it will be generating it'll be finding that 7 by randomly fuzzing, since the value 7 doesn't actually appear in the source code. And once it's done running, we can see that it does in fact say 7 crashed the source code. Okay, so this example is going to show how our constraint solver can solve some simple constraints inside conditional statements. And we can see here that we're trying to get inside this simple block of code that has a divide by 0 crash. And it's going to crash when arg0 is equal to ab1. ab1 wow dot compared to arg0 plus wow. So our constraint solver will solve that and input AB1, and we'll see that here briefly. So I'm just going to real quickly fast forward over some of the startup for this, finding the file, and we'll get right into it. So here you can see that the bug did in fact crash with AB1 as an input.